to or welcome back to my channel. I'm sorry I haven't been uploading for around 2 weeks, and I'm really happy to be back to upload again. Today we're gonna work on the question network delay time. It's a medium level question on LeetCode, and let's read it. So basically the question states, you're given a network of n nodes labeled from 1 to n. You're also given times, a list of travel times as directed at just times I equals u vw, where u equals the source node, v equals the target, and w equals the wait. W equals the time it takes for a signal to travel from the source to target. So w is like the time. And then we will send a signal from given node k, return the time it takes for all the n nodes to receive the signal. If it is impossible for all the n nodes, then we return -1. Let's look at the first example they give us. This is our graph, and then let's look at this. 2 is the source, 1 is the target, and the time it takes from 2 to 1 is 1. 2 to 3 is 1, which is shown here. And then 3 to 4 is also 1. It takes time 1. And here. Basically, n equals 4, so n is how many nodes there are. There's 4 nodes here. And k equals 2. K means the node that we're starting off on. So when it equals 2, at the first minute, it goes to node 1 and node 3. So this is the first minute. And then at the second minute, it goes from node 3 to node 4. And at the second minute is when we've reached all the nodes, like all nodes receive the signal. So then the output would be 2, which is correct. Looking at this question, we know that our objective is to find the fastest path from node K to every other node. And this is a typical use case for solving the single source shortest path. And to solve for this, we can use an algorithm called the Dijkstra's algorithm. Basically, the Dijkstra's algorithm uses like a BFS structure and a min heap, and it solves for the single source shortest path with non-negative weights. I'll just write it quickly. Min heap. It's used to solve for single source shortest path with non-negative weights. For negative weights, we have another algorithm. I'll use that algorithm later on in my other video. And basically, the main idea of the Dijkstra's algorithm is we will start from a point as a center and gradually expand outward, updating the shortest path to reach other vertices. And it basically uses like a greedy approach, and at each step it selects the min weight from the currently reached vertices to find the shortest path to other vertices. And in a typical BFS, we use a queue, and then it broadcasts the signal from the visited nodes in a first in first out manner. However, in Dijkstra's algorithm, Dijkstra algorithm, we would use something like a priority queue. Priority queue. I'm sorry, I can't spell. Priority queue. To traverse the nodes from the min to the max time required to reach them, and it will always start with the min node. And that's why in each iteration we will visit the node with the shortest travel time, and that's how it can help us find the fastest time path first. So let's start writing our algorithm. First of all, let's create an adjacency list, and to create an adjacency list, I'm gonna from collections import default dictionary, and let's create my adjacency list here. Equals default dictionary of lists, And then I'm gonna populate my adjacency list. So for these things, source, destination, weight, time, and times, I can populate my adjacency list with the source dot append. I'll do this will be sorted for each one. It's gonna be sorted by time and destination. So time and destination, it's gonna be a pair for each source. And next, I'm gonna have a visited set. So visited equals set, and I'm gonna create my priority queue, which is gonna initialize at time 0, and then I think it starts at node K. So I'm just gonna call it a queue equals 0 and K. K is given to us through here. And yeah, I think I can start writing my BFS. So I'm gonna do while queue. First we will pop off the element in our list, in our queue, so time and node equals. We're gonna use a priority queue, so heap queue dot heap pop queue, and then we check if this node that we popped is already visited. So if node in visited, visited, we don't do anything, we continue. Otherwise, we add this to our visited set. So visited.add node to make sure that we don't visit the same node again if we've already visited it before. And then we check for our base case. So what's our base case? We want to check if we have already reached every node at this time. So if let's say length of visited equals n, which is given to us here, then we want to return the total time it took us, right? So we return time. And otherwise, we can, I think, finally go through all our neighbors and push our neighbors onto our priority queue. So for neighbor time, neighbor time and neighbor in adjacency list, node and then we can append it to, so heap queue dot heap push. I believe heap push takes the queue first, and then it takes what we're appending to our queue. So we would have our neighbor time. We not only need our neighbor time, we need our neighbor time to add our current time, because it'll be a total time added together, right? So our neighbor time plus, I'll do it at the front time plus our neighbor time with the neighbor as a node. And then I think this is it. And if it hasn't returned here, then finally we would just return -1 at the very end. Thank you so much for watching, and please let me know if you have any questions.